the burritos are good. It's a pretty easy order. So I'm still trying new catering things to try to. So I've never eaten Del Taco before in my life. Didn't believe that. This is gonna be the first time.
How long have you lived here?
I mean, a long time. I've driven by it for years, but I just have never gone in. I have nothing against it either. It's just one of the things you're just like, maybe I should go there, and you think that 200 times in your life and never do.
Maybe you should go there. And what are the vegan options?
I have no idea. They're veggie options. Which
I just.
I know they have like veggie burritos. I don't know if it's vegan because it's Mexican beans, but
It has a hot dog taco either.
yeah, I don't know. Well, you could, if you were here, David, you could have it. Pretty good for catering. So you can get burritos for like $70 or something, which anymore is really good. All right, so we'll go ahead and get started. Thanks everybody for coming. I'm gonna go ahead and kind of just go through the light stuff here. There are still, I'll reiterate again, there's food there. Feel free to take the chips, and there's plates now if you want to dish out some guac and salsa and all that good stuff. Go ham on that. Oh, hold on. The actual slides here. Okay. We're not actually recording through these mics.
We
but
are.
Are you recording through it, or are you?
I didn't give him the lapel.
Okay. So we are recording through these mics. All right. It changes every time.
It really does.
These positional mics are really, really good. If you whisper, they will find you, and your whisper will be committed to YouTube for posterity. So only say nice things, and you'll be okay.
Until the recording stops, and then you can be mean, but
Then what-
not to the
Yeah.
speaker.
There will be a position at the end, the time at
Still
the
have to
end
be
of
nice to the
the.
speaker.
We're always nice to the speakers, but we're not nice to each other once the recording stops.
Exactly.
Necessarily. Talk to us. I really should change the slide, but haven't been bothered. So normally there's this paper call, but really the way we source this is people go through the Slack. If you've not opened on that, fortutah.tech, you can go join our Slack through that link. There's a link to Slack, and you just go to the Golang and myself or Brandon Atkinson, or just post in there, say, I want to talk at the meetup, and we'll get you. I've had a long-standing policy of, if you want to speak, I will find a way to get you to speak. It doesn't have to be long. It doesn't have to be like a 5-minute talk, and we'll pair you up with somebody else, or it can be a full one, or whatever. Like I want to provide that platform for people that are like excited to speak, and we'll find a way to fit you in. And it's really easy, as our current speaker has mentioned. There is a on the go channel. There is kind of a wiki. I think they call it a canvas in Slack, of all of the topics, all the kind of like I've gone through and like found everything in the standard lib and said, here's some things that I think are worth talking about, kind of grouping them logically. And you just go down that list of standard lib stuff until you find something that speaks to you, that you think you want to talk about, and then talk about it here. They're always really popular. You always get a chance to learn something if you know a package. It's a really great way to do it. So that's what we're doing this series of standard lib talks. There is still pretty good activity on the jobs board, and that's kind of a formal Slack workflow thing where you go in there and submit those. So if you're looking to hire somebody or want to get hired, lots of good stuff in there still. I have to mention, because they're buying a food, thank you, Weave. They are providing the facility, they are paying for the food, and there are openings for Weave. A few in the US, I don't remember moment what those positions are, but there are. Weave is actually in a pretty,
Principal data engineer is one of them.
yeah, so like there's some good
LinkedIn
stuff.
wants me to apply.
We're in a pretty good hiring push right now. So if you want to work at Weave, it's a fantastic place to work. You can come into this lovely building, or depending on the team, you don't have to. So there's, even though it is US hire, there's lots of remote opportunities in the US. For example, I only come in here for this. I don't even come in today. I didn't work today from the office. I worked at home and then I came in. So we're really, really open with our work policy. And that's it. So talking about the sync package, I'm going to hand it over to Brick. So, thanks, Brick.
I'll share my screen in a second. But first I wanted to intro a little about who I am and why I picked the sync package. So I have never written Go code professionally because traditionally I was a math major in college and then I worked in data. Everything in data, at least for me, was Python and a little JavaScript, because everything's a little JavaScript apparently. But we did Python, and that's what I learned. So I did did 4 or 5 years of development, and I had never written a line of statically typed code. Every time I had to do anything concurrent, it was with a prayer, and I hated it. I really hated it. I found it frustrating. I found it imprecise. I found it confusing. In the beginning, it was very easy for me to write code, but at the end of the day, I often found myself very frustrated finding bugs. And then I listened to an hour-long lecture by Bob Pike talking about like the idioms of Go.
Right.
And I just listened to him, and it sounded half like a lecture, half like a rant. At the end of it, I thought, whatever he wrote, I want. Like, he hooked me. So I started writing in Go. And the first thing that I thought of was based on what he had talked about. Everything was throughout that talk was just constantly concurrency, concurrency, concurrency. And I thought, well, I should start playing with concurrency. And I found it unbelievable. Because my experience at Python, where I came from, was every time you want to do anything concurrent, it just felt brutal. And they didn't play well, and it was basically just parallelism. And I didn't know the difference between parallelism and concurrency, but I was very excited, and it naturally led me to data races. That was the next thing that I encountered. So I encountered data races, and then encountered how to fix them, and that was with the sync package. And the sync package, I thought, starting there, taught me a lot about writing Go code correctly. And I say that as someone who I don't think writes Go code correctly, and I haven't been doing it very long. But as an example of what I mean, I have this. So I have Eric as a volunteer. Can I get one more volunteer? Great. What's your name?
Donnie,
Lonnie. I heard the microphones will pick you up, so
I can yell it, not.
I'm just gonna demo.
It hears you.
Perfect. So I'm gonna demo what this does really quick, which is, we're just gonna lead through this really quick. So I'm a counter, and my counter's at 0. You read it, right? So what's that?
0,
Great. And you increment. So what's it at now?
1.
All right, I'll be at 1. And then you said Donnie.
Mhm.
Donnie, you read it.
Okay, theoretically, it's at 1,
Great. You increment it.
2.
Great. I'll be at 2. That's what I thought it should do. So if I did it 1,000 times, the idea being I could spin up 1,000 Go routines that theoretically would work concurrently and increment my counter 1,000 times. And
Theoretically.
yeah, theoretically. It was interesting. Change my screen. Okay. And it did. So instead of outputting as 1,000, an output is 953. And of course, that should be, I think that's, judging by the nods I'm getting, that's pretty obvious to the room. So what we just went through was this, which was a Go routine reads the value and increments it, reads it, increments it, reads it, increments it. But that's not what actually happens. What actually happens is this. So counter's at 0, you increment it, what's it go? You read it, sorry.
0.
Great. And then Donnie is impatient. Donnie reads it too. What's that?
Still 0.
It's at 0. And then you increment it and it's at 1. And then you increment it.
That's at 1.
That's a data race. So the data race is things aren't working sequentially like how I hoped to when I wrote the program. And you can see that here. So instead of these colors representing the Go routines, working one at a time and making sure not to overlap, and then read data before other Go routines finish writing that data, they blend together. And it seems to be 47 times. Basically, a write was lost, an increment was lost. So the solution to this is the first and most important part by my understanding of the sync package, which is a mutex. So a mutex stands for mutual exclusivity. Okay. The idea of mutual exclusivity is if things are mutually exclusive, they can't both happen at once. So if I flip a coin one time, it can be heads. It could also be tails. It can't be both. That's mutual exclusivity. So that's what mutex stands for. When we create a sync mutex, we use it to ensure that things don't happen at the exact same time. They happen sequentially in an order. So our counter first was initialized at 0, and then 1,000 times we create these Go functions that are adding 1. And then we wait a little bit and we print it out. with the sync.Mutex, we create a mutex and then we lock it in the go routine. What that means is we're in the go routine, and before it has the opportunity to touch counter, which is our shared data capable of having a race condition, we're going to lock a mutex. And what that means is if a mutex is locked and any other go routines attempt to also lock, they're forced to wait. Then they increment the counter, the go routine that has control of the mutex, and then it releases control of the mutex for another go routine to then gain control, increment, and then release. So that's what this looks like. So if we run through this again, right, and we're trying to stop impatient go routines from ruining our data, what happens is Eric, the speed demon, gets here first, and you lock, right? And then you read the counter. What's that at?
Yeah, 0.
And then you, Donnie, show up.
Attempt to lock.
Yeah, you attempt to lock. And I say, you can't. You're just gonna wait. Yeah,
And I sit in the door going, please let me in.
that's exactly what you do. Yeah, in fact, you'll even starve, according to the Go docs. And then you're gonna increment because Donnie hasn't done anything. You're gonna go to 1. You've done your job. What are you gonna do next?
Free.
You release that lock. He's been knocking at the door. He gets control of the lock. He's going to grab hold of it
1. Prevent to 2
and
and unlock, I guess.
And unlock it.
I'll allow those other 998 go routines in.
I will tell you, it's very nice of you to release the lock after because many of the go routines I've written never did. And you can see that difference here. So here, we still have that 953, but the run after, and it's all 1,000. No race condition, yes.
Yeah, I was gonna say, one of the things that I see pop up commonly in code is lock and then a defer unlock. To help prevent that situation where you deadlock your code on accident. So you would have to, in this case, well, actually, no, it's inside of a Go function, so you'd be fine.
But I think that's the, I don't know, isn't it anti-pattern? That seems like the exact right pattern to me.
Gonna say.
It's good, especially if
If it's an anti-pattern, please tell me, because I do it.
Your exits at the end of the function and you don't need it after the end of the function. You need it unlocked after the value is changed.
Correct, so it does
If you scope your
require,
function well, then
This is-
defer.
That was what I was gonna say. It matters how you've scoped your function, because if it's in a huge function and your defer is gonna happen long after you should have unlocked it, then that's not going to, like, you should have it well scoped so that defer exits correctly. But if it's too big or too
You should
small-
also only be locking when you absolutely need to, instead of just lock at the beginning of the function and then
Right.
maybe do some weird thing and panic or whatever and lock things.
Yeah.
Wanna do
It's
the weird?
helpful with the panic. If you have to recover from a panic, then that will.
Well, I think the panic point really brings up a perfect example, like if counter one was able to panic, then you have a situation there where if that panics, your unlock never happens. So that's why the defer is like the pattern is like, if your thing in the middle can panic for any reason, defer will always unlock.
So for the sake of the remote listeners in the recording, I'm going to summarize what just got talked about. So right here, I unlock at the end of the function. So instead of unlocking it, I can use a defer. If you defer something, it will automatically execute at the end of a function. So I could have done that here very easily. And the reason why you use defer is because your function doesn't always have one exit condition. It doesn't always exit in one place. So if it exit multiple places, instead of ensuring that you unlock at every place before you return, you can just defer and unlock and it'll ensure that that always happens. However, as the point has been brought up, that isn't always smart because sometimes you have these giant functions. And if you defer and unlock, you're doing all of this other stuff not relevant to the data you're trying to protect and locking unnecessarily. So there's go routines starving at the door like Donnie, waiting for an unlock. And the only reason they can't go in is because of bad programming, not out of the need to protect that data. And, right, did I miss anything with that?
Sound great? I think that's great.
So this is, by the way, what that looks like, which is, by the way, the colors, if I didn't make it clear, represent the go routine. So the red one locks, it reads, then Donnie shows up and he waits. Then we increment unlock, and then he can lock, read, increment, and unlock, and so on. So that's a mutex. And we'll come back to mutexes in a little bit, but in case anyone gets bored and is about to quit, I just wanted to get through the two minimal things that were the most important, which are basic mutexes and weight groups. So
I was about to say on that top one, I was like, you could use a weight group instead of doing the sleep, but then maybe that was, too much and it was detracting from, but I was literally thinking you should use a weight group.
appreciate that. Yeah, I'll tell you, I'm also looking at it thinking I should use a weight group. It was hard to write. So this is the code that we had before, and here is the code that we have now. So I deleted my time import and my sleep. So I have my mutex, I have no data race, supposedly, and yet I have 1,000 on the left and 987 on the right. So what happens is, well, Brick, you protected the counter. No one's writing to the counter out of turn. And that's true, but I have an early read. And that early read is a little sneaky because it's not even wrapped in a go routine. That early read happens here in my print statement. So what's happening is I have a go routine that's incrementing, and this print executes, and then I have go routines that continue executing. So actually, if this function was allowed to run all the way, the counter would still be able to reach 1,000. But I finished running this program before all the go routines could finish, maybe. And I definitely ran this print statement before they could all finish, which is why it goes to 987. This is the situation where you would bring in a weight group. So a weight group allows you to ensure that when you spin up a bunch of different go routines, and you need to ensure that they've all finished executing before you move on to a next step, that you can easily track. And you track that by taking I could have explained that a little more clearly. You basically instantiate a weight group, and then you add to it when you initialize a go routine. So when you say, I'm about to start a concurrent process, I'm going to add one to the weight group to tally. I've added one more that I need to wait to finish. You had to do a second one, you add a second. You do a third, you add a third. And then when all those go routines finish, what they will do is they will decrement it. So they will say, weight group's at 3, I'll bring it down to 2 because I finished, I'll bring it down to 1, I'll bring it down to 0. And what this guy does here at the end, instead of time sleep for 200 milliseconds, is he's going to wait until the weight group's at 0. And that's important. And I'll explain a little bit why in a second, but he's going to wait till it's 0 and then print. And because this weight group waits until a weight group has added 1,000 times, incremented 1,000 times, and decremented 1,000 times, it's going to get that complete run of 1,000. The same way as the time sleep. If you notice very carefully, by the way, they don't show up at the same
I was
time.
about to say, but it'll go faster because it's not waiting for an arbitrary amount of time. It's executing as soon as it can, as soon as it hits 1,000.
Yeah.
Why it's better.
Yeah, and if there's one thing that you learn switching from Python to Go, is that the Go programmers suddenly care about milliseconds in a way that Python programmers don't.
Arbitrary hard-coded sleeps are always a good idea. Concurrent programs.
I have one subtle thing too, and I think it's important. If you swap lines 14 and 15 on the right side, you will introduce a different new bug.
Yes, okay, so I would love to explain that. Yeah. Thank you. So Carson brought up a very good point. So let's imagine I swap lines 14 and 15. So now adding one to my Go routine is adding one to my weight group happens within the Go routine. So this is what could happen. Weight group number, so this weight group is waiting for it to be 0. Now, theoretically, what you would hope would happen is it's adding and decrementing, adding and decrementing, adding and decrementing, but it's adding faster than it decrements. The value stays above 0, and that weight group is not going to finish waiting until all 1,000 Go routines are finished. But let's just say Go routine number 1,000 is incredibly slow to start for some reason. What you could have is 999 Go routines, add one to the weight group, 999 decrement from that weight group. The wait finishes and the counter prints. And after that happens, the 1,000th Go routine finishes, starting, adds one to the weight group, adds to the counter and finishes, in which case things wouldn't have happened sequentially and the print would only be at 999.
That's not theoretical. I've seen that bug where people, because it's so, you're like, why is this weight group outside the Go function? It's a very easy thing to do is to,
So because that's
Asynchronous.
so easy, is your next slide gonna be the wait group.go?
It is.
Okay.
The other thing that I'll, is if we're talking about milliseconds, we might as well talk about microseconds or whatever microseconds would be. And instead of adding one on every line, another thing I could do is on line 12, I could have just added 1,000 to the wait group. But what's really important is that you just ensure that whatever line is adding to the wait group happens in code that you know must execute before the wait. So anything that happens in the go routine is not guaranteed to execute before you reach line 22. So we take our out of the go routine and we ensure that we're going to add the 1,000 that we need to. And that the only way that wait can reach 0 is if there's 1,000 decrements within the go routine. So you see that here, but I mean, frankly, we don't really need it. So
Oh, yeah.
nicely done. So
So on the same wavelength.
Everybody acts surprised.
this is the translation. So it's pretty recent, right?
Yes.
That they added wait group.
I think it's 126.
No, it's 120.
Or was that 125?
you guys are nerds and I love you all.
It's,
We're arguing about what version of feature, like a minor
So
standard lib
excited
feature
about
came in. Go, sorry.
That's another parallel to Python. Most production code I've seen in Python is still on 3.10, so it's pretty. It's 3.10, you can use it, anything added after is just kind of a myth, but we'll call that.
At least it's 3.
So what a wait group go does is it allows you to take away the adding and deferring the done. So what you do is you just say wait group.go. Oh, and actually instantiate the go routine and you just say wait group.go, include your function and it'll run the function in a go routine, automatically add to the wait group and automatically defer decrementing from the wait group at the conclusion of the go routine. So I actually have the code, so they're the exact same. I mean, really the exact same. And you can see here, I grabbed this. This is the actual code for the wait group go method. So I often am a little scared to actually look in the standard library and see what's going on, because often I just look and just see these mile-long functions or methods. But it really is just, and it's funny that it took so long to add it, but you just input a function and this is attached to the wait group and it literally just adds it, runs the function, or sorry, adds it, defers decrementing it, and then runs the function. This is the whole thing. So if you really wanted this feature in whatever version you have, all you have to do is create this little method and override your standard library. No big deal. So that's wait group. Any comments? Sorry, Eric.
I was just thinking, like, I also thought it was kind of strange that it took this long to add this to the standard library, but I've also known, and I don't know what the conversation was about this, but I also know like that Go is a very not batteries included, like they want to be as basic as possible with standard library, and their philosophy has been like you can do it yourself, right? A little bit of copying is better than a lot of abstraction or something like that. So I'm interested if what the conversation was around that and if it was a long conversation, because it kind of goes against their philosophy. Like you could just add this to your repo and just like have it be a public function and do that, or versus adding it to the.
You can see this conversation. This issue had the whole thing, and actually the entire solution was in the issue.
Have you seen it?
Yes.
See what it,
Yeah, I mean, I definitely did a while ago.
I think they do have a pretty good threshold for like, my guess is, if I had to make a guess, they're like, this is a small number of things where the order and positioning very critically matters and it's an easy bug to introduce. So it's not just a convenience thing. You have to make a case of like, this would prevent, this is a valid guardrail for dumb developers because we're all dumb developers. So let's just put that in there. It's not convenience. It's
I think to
prevent subtle bugs.
the main argument. We'll mess that up all the time.
I think there's an element of that, but also this structure it was absolutely everywhere. Or you would have to write this function everyone does it the exact same way almost. If you need to do it differently, you can, but this exact pattern was so repeated. Like for other things, there's just enough flexibility and variation where it's not quite consistent everywhere, but this is so common that it just seems warranted to it just should be a built-in wrapper because of how common it is. But also, more importantly, it saves you.
I think they've done, yeah, they did that exact thing with like the ranging over numbers, just ranging over an int that you're doing there. That was not there like a year ago. And it just had to be proven like, it's so often and so convenient that, yeah. So it is, I like, actually, I love that they don't put a lot in there. Like, that's actually a good thing to me that they're like very persnickety about not bloating up their standard lib with stuff we don't need.
Yeah,
Me too.
I mean, I recommend you actually go look, I mean, it's really enlightening to go look at the building issues and proposals, and they have, you can see all the proposals they're working on. They have a discussion that shows all the ones they're talking about, like the other ones that they throw out.
It is going to be part of those.
Thank you. Okay. Sorry, anything else on weight groups?
Sorry, I had one more thing. Are error groups
Yeah.
in a different package or are they,
No, it's the same package.
are they the same?
It's
They're
in-
index.
Or what?
Error groups. They're
They're
not in
group
X
is in
anymore,
X.
okay?
They're the X, I thought they were in weight group.
Thought they're standardized now. So there's a different version. So one of the shortcomings you'll notice with weight groups is if you need to return an error from your function, you can't. There's no like really easy way to like spin off 100 of these and then get a list of the 10 out of 100 that failed.
I don't know.
They're
I just
errors.
know I don't use
Um,
weightgroup.go. I use error group now.
Yeah, and so there is a new kind of sibling package called error group that has a very, very similar interface, except for that .go, the function returns an error, and the total, the .weight returns a list of errors, a slice of errors. Yeah, right. So I couldn't remember if it's not in here, then it's probably then it's X. If it's not in your thing, then it's not in this package, but there is an equivalent.
I'm quite sure it's not in the official sync package, but yes,
It's in
it is.
/X.
It is a common.
But I use it
It might be an experimental still. I use it all the time, so.
only.
It's extended.
Doesn't mean the same thing, though, yeah. Surprisingly stable for what it extent.
Anyway, that's an aside.
So I'll just recap what that is. So what was referenced was error groups, which I've never used, but if I understand you correctly, the idea of an error group is you can instantiate an error group instead of a weight group. And then when you call weight at the end, you get just a slice of errors back.
Good, done.
And the go function that expects instead of just an error function, it's a function with a return error. It has to return an error, even if you don't want to. I mean, well, if you want to, but
You can return nil.
but that's the signature.
Perfect. Okay, so now we're on a read-write mutex. So the problem earlier when we were doing races was rights. The idea is if a variable doesn't change, then if 1,000 different goroutines read it, there's no liability because it's going to be the same thing. The only time where your reads and your writes can contradict and then cause problems is if you have writes that change the variable in a way that's unpredictable to the other goroutines. And to account for this, we have a read-write mutex. So I'm going to show an example of what is useful about read-write mutex. This function is going to read from counter 10 times. You can see spaced 300 milliseconds apart. So it's just boom, 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 boom. And if it runs 300 milliseconds apart 10 times, it takes 3 seconds. And you can see that. Is that easy for you guys to see? Do I have this too?
That's fine. Great.
So it takes a little over 3 seconds because it's a bit of overhead, but 300 milliseconds times 10 is 3 seconds. And you could do this. You could have the mutex lock. You could have the 300 milliseconds of time you need with counter and have these things just all stack up and take 3 seconds to do it. But this again isn't Python. We're going to use a read-write mutex, and a read-write mutex allows for simultaneous read locks, but sequential write locks. So what that means is you can have multiple goroutines read a value at the same time. but there will be no reads while a write is happening and no other writes while a write is happening. So if we just make a small change of changing our mutex to a read-write mutex and changing our lock into a read lock and a read unlock, then it's just going to instantly do the 10 reads of the counter, and it takes us a little over 300 milliseconds, right? So we have the same protection over the data with our reads, but because the other reads aren't a threat, they can run concurrently. Here's an example of reads and writes working together. So I'm going to cover up this import, but I have this function. This is the trickiest thing I've shown yet, but the idea is I'm going to run 10 times and run one of two different go routines. The first one is a write. So it's going to do a write lock, which is just a lock. It's going to sleep for 1,000 milliseconds because writes take a long time. It's going to add 25 to the counter, and then it's going to unlock. That's going to happen start of the time. Here, I'm going to read lock, sleep for 300 milliseconds because they're faster. Going to print the count and then unlock the read. And what that does is when I click run, there's a spurt of reads that are reading the 100. Then a write happens, which is that 1,000 millisecond pause because writes can only, when a write's happening, only one go routine gets to touch counter, and that's the write. And then all the other reads are going to run before any of those other writes get to happen. Does that make sense? So if this was to happen without the read write lock, I would have that additional 300 millisecond barrier. If this is going to happen without a mutex, then I would not be able to accurately read the current state of counter. So this is the happy medium, which allows to prevent the data race while being able to have the simultaneous reads for speed.
All right, you might have answered my question while I was formulating in my brain. But is there a write lock, or is it just lock? Because like write needs to read.
Okay, so that's a great question. There is the write lock is basically lock. The reason why you would lock is because you're going to change the data. So the idea of a write lock is only one thing should be writing two data at a time. And while that's happening, you shouldn't be reading it. So that lock is not called a write lock. It's just called a lock because you're not just locking it for writers, you're locking it for everybody. Make sense?
I have a question about this, since you've dug in, I have never done it. Is there some sort of prioritization with writes? If I've just got things writing nonstop, no one gets a word in edgewise for, like, if you're like, got readers and writers all trying to do it at once, does it just drip them in alternately? Is it like writes always take priority? Like, how does it prioritize that? Like, cause I could just see, like, if you have this endless stream of readers and you need to get it right in edgewise, how did you do that?
Very much. So anyone have a better idea of this than me before I get my crack at it? A good question. Okay, so one thing that I'll cover just because it's useful and it's not a direct answer to your question is something about mutexes, general mutexes, which is again, not an answer to your question, which is starvation mode. So generally what happens is you have a list of go routines waiting for a mutex. By default, the one that is most recently waiting is the one that will grab the mutex next after it's been released. Problem with that is if you have this stack and you're constantly grabbing off the top of the stack, there's go routines that are just going to rot at the bottom. So there's this mode called starvation mode, and I don't know a lot about it, but what I do know is if a go routine's been waiting long enough, it's going to prioritize it and allow it to jump ahead in the queue. My assumption is something like that exists for read-write mutex, but I don't know anything about it. Obviously, if reads are locking and unlocking in parallel, it's possible for them to just permanently lock it. My understanding is because reads are so fast, to the degree, maybe it's just, well, that's theoretically possible. It's not something that you have to be that afraid of, but I just don't know.
It does say they're separate and that write is preferred.
Right.
Separate queues.
A lot of times, surprisingly, a read-write lock doesn't improve performance. One of the reasons why is like, aside from the scheduler, which I don't know what weird stuff it's doing, you just think if you've got a read lock already and somebody asks for another read lock, you give it to them, right? So now they can share the read lock. So you can have lots and lots of readers, and they're all gonna be doing their thing. And any writer that now wants to get a write lock has to wait for all the readers to finish their thing. So in that sense, it's not very like fair, because it has to wait for all the huge batch of readers. If there is a huge batch of readers, and ideally there is, because that's why you're using a read lock, is because you've got lots of readers, it has to wait for all of them to finish.
That lines up a lot with what I'm pulling out of my brain of what I think I remember about this, which was read-write locks are primarily for really, really read-heavy loads with the very occasional write.
And now what happened, the question I think people are asking, I don't know the answer to, is like, say you have a bunch of readers that are holding the lock and then a writer waiting in line. And then you have like, you know, a series of readers and writers come waited line too. Like, is there any sort of ordering or prioritization or even coalescing of those readers? I have no idea.
Yeah, it says if
Probably
any,
varies from runtime to runtime.
for Go, if any readers are actively holding the lock, any new readers can immediately join and read concurrently. If a writer arrives, as you said, it has to wait until it can take the full lock, and then it has priority. It has priority kick in FIFO. So the first person that requested it should get it. And if you're doing casual updates of data, it works great. You can then simultaneously read all you want, and you'll stall for a little bit when you write it, assuming that there's some like transaction deadline on your read side as well. And if there isn't, then you can still start.
Thought that like in practice, what I do basically every time I personally have a situation that like seems like it probably would benefit from a read write lock, it's really an atomic swap sort of situation. But again, that's just like those are the things that I do. So it's usually like config data structures that you want to be able to update at runtime. They've got lots of readers. You need to be really fast. They're getting hit all the time, but you do need to be able to update them maybe once an hour. But usually that like an atomic swap ends up being cleaner.
I appreciate it.
Great, thank you. I would summarize that if I knew what it was, but I don't.
You got him on
Got
mic.
it.
Okay, so there is the read write lock, and now we have a read locker. So the idea of a read locker, sometimes you want to give a function basically just the ability to read. You don't want to give it write locking and write unlocking permissions, or you have an interface that requires a locker that only has the lock and unlock methods, not the read lock and the read unlock methods. So in that situation, you can use a read locker. And my understanding is basically here we have a read write mutex that we call read write mutex. Now this isn't standard convention, but what I'm going to do is I'm going to call the standard one the write mutex. But remember, it can do both. It can do write locks and read locks. And then the next one, the read mutex, which is the same mutex, but just the read locking capabilities, not the write locking. Then in our function, you can see I don't use read lock or read unlock. What you do is on my read write mutex, which I called write mutex, I can lock and unlock. And then on my read mutex, I can lock and unlock. But this go function, no matter how bad I am, does not have the ability to write lock.
Seems like a really weird interface for them to define.
I think it makes sense though, because if you're just taking a locker, right? If you just want a mutex, I think the caller should be able to pass in a rewrite or a read. There are definitely situations where you would want to be able to define just that interface instead of having to account for both of them.
You provided the mutex you think I should use, whether it's a regular sync or a one that is capable.
You decide what kind of mutex you want. All I know is I'm going to need to call a lock and an unlock, and you can define if you want that to include writing or not.
And funnily enough, what I wanted to showcase is that they run the exact same way, but no matter how many times I tried, there was no, they don't. Because to be fair, it doesn't, you run it twice, it runs differently, but they do. They're the same. And then the next one is a try lock. So try lock, this is a completely different function. So I have my counter initialized at 0. I have my mutex, I have my wait group, and I'm running these two go routines. And each of these go routines are either going to do my right here or my read here. Okay, so this is gonna be a little bit of a bear. This one, this go routine is going to have a local variable called local counter. It's gonna lock counter and read. And then it's gonna unlock the mutex, unlock counter, and it's gonna print it, and it's gonna sleep for 300 milliseconds. So basically, this thing is just going to keep looping and reading counter and printing counter. And the reason why I'm doing this is the kind of the idea of like polling, like the idea that you want this thing to every 300 milliseconds, so be able to supply you with a new value. Okay, I want this thing to operate at every 300 milliseconds. That's my goal when writing this code. Every 300 milliseconds, print the value of counter. And if counter is currently taken, just print the last known value of counter. That's the goal. And then on this go routine, it's going to 8 times lock it, sleep, add 1 to counter, unlock, and sleep again. So this guy is locking, waiting for a while because writes take a while. And it's going to add 1, take a break, and do it again, right? So, but the goal of this is to really show every 300 milliseconds, I can print the last known value of counter. That's what I'm trying to do. I don't do it. You see here that, oh, pause, oh, pause, oh, pause, oh, pause. And the reason for that is because while I have this sleeping every 300 milliseconds, it's also waiting here at the mutex log. So there's a couple different ways to go about it. Basically, how can I make this thing run every 300 milliseconds very consistently? And the simple way to do it is with the try lock. So it's a very simple change from what I'm doing here. Instead of a lock, I'm going to do a try lock. What try lock does is it's going to attempt locking the mutex. If it succeeds, it returns true. If it doesn't succeed, it returns false. So it's going to attempt locking on my counter, and if it fails, it's going to print the last known value of counter and keep going. And then sleep at 300 milliseconds. It's going to continuously do that. It'll try, but it won't wait at the door like Donnie was doing. If it can't lock it, it'll just skip. So it's going to keep looping and every 300 milliseconds print. However, if the lock is free, it's going to update its local understanding of counter, and it's going to release the mutex. And this is going to allow us to every 300 milliseconds print in that consistent polling rate that we want. Does this make sense?
Yeah, that's actually a really good way to explain that, like.
Thank you. Does anyone have any comments they'd like to make on the try lock? That's this pool. This is easily the least fun function that I have for the day. Because if you want to prove why you need pool, all of a sudden you're doing benchmarking. But I'm going to skip a lot of this. So if you want the whole function, it's there. Oh, also, by the way, wait, do I still have it saved? Huge. If you go to that short URL, you can pull this up yourself. This is just public.
What's the short URL?
Oh, geez. I have, oh, right, you can't see it. Okay. So if you want it, I can read it out to you right now. This is the one time to get it if you want to type it in.
You can put it in the meet idle.
Oh, that's so much better. That's obviously the thing to do.
I was gonna ask at the end what you were using to present this.
I am so curious.
I really like this, this interface.
Oh, thank you. I just made it, or I should say I half made it and then Ellis half made it as a conglomeration. But anyways, so this thing is a test and we're not going to get into what tests are. What we are going to get into is benchmark without pool and benchmark with pool. Right? And all we're doing here is we're going to create basically 64 kilobytes, an array that's 64 kilobytes long here and here. But this one doesn't use a pool. So this one, every time it's just going to make a fresh array and do work with it. And this one is going to create a pool of that 64 kilobyte array once. And then it's going to loop, do the work, and it's going to grab data from the pool and then release data back to the pool. The reason why you would do this, I'll explain why you would do this first. One, I would love input because I don't really know. But basically what it comes down to is what this first one does without pool is it continuously allocates memory. And allocating memory is a giant pain. Actually, so I taught programming for like 5 years at a Boys and Girls Club, which is pretty sad because again, I only knew Python. But I got pretty good at the hands-on demonstrations. So here's my idea, right? Your guys' hands are my memory, right? And I am in desperate need of various types of work that you can do with hands, one of which being high fives. So there's two ways to go about this, which is to either say, every time I want a high five, I need a high five from somebody. One of you raise your hands, I walk over to you, I give you the high five, and I walk all the way back. And then I say, I no longer need that hand for a high five, it can do something else. The other option is to just take my man Eric right here and say, Eric's right hand is my high five hand. So I need a high five. And instead of returning that to memory and deallocating it, I just keep that hand on standby. So that hand doesn't do anything anymore. No eating, no phone, no nothing. And then if ever I want to, and I'm bored, but that thing stays there and it saves me time from not having to allocate every time. I'll deallocate.
Oh.
Right. So that's what a pool does, is the idea is you can limit the amount of memory that you need to allocate. We're going to see that with a little benchmark here. There's going to be a lot here. You can ignore most of it. But right here is the valuable number, which is, I believe, allocations per operation. And if you look, there's a drastic difference in the amount allocated because this thing is allocating basically the whole array every time. This thing is allocating the array once, and then it's just continuously reusing it.
I think the other benefit to reusing your memory, if you have something that is going to be operating that hard, that'll probably be like libraries for, reading and writing stuff, is it reduces the garbage collector pressure that can build up over time. Because at some point the garbage collector is going to have to reclaim the memory and it's going to slow things down to do it. And if you have a pool of memory that you can just infinitely reuse, then the garbage collector doesn't have to stop and reclaim it all the time, and it will improve performance.
Thank you. Yeah, I guess when I deallocated, that wasn't very.
It wasn't reclaimed until the garbage man comes around and says, "You're mine now," and sometimes you reuse it again.
Yeah, because that shouldn't be my job. Another thing, as an example of, I'm sorry, what's your name?
Brooke.
Of what Brooke is talking about is I had to do a sync because if I didn't do this sync, the numbers are basically the same because the compiler did a bunch of magic that made that I was really needing all of that. Basically not just do the efficiency for me. And chances are, if you're trying to use pool, the compiler is just going to take care of the.
That is a thing that bites you with a lot of benchmarking in Go. It's like the compiler can really screw up your benchmarks if you're not careful.
Yeah.
Oh, yeah.
Compiler.
I'll just kind of throw it.
I know.
I do a lot of benchmarking and performance optimization in Go. I use pools sometimes. So you should never just think, hey, I want to use a pool here because like maybe it'll make things faster. Just profile and you see like runtime.scan and runtime.mheap everywhere. And that's when you go, oh, like the garbage collector is busy doing memory stuff. And then you look at like bash grind or the pprof tools and you go, and it's doing memory stuff there. And then, you might just lift a variable out of the loop, so you don't make it like, allocate 20 times in a loop. You might do a bunch of things and pool's one of them. Sure.
Name?
I'm Shane.
Shane. Thanks, Shane. So a point that you're making is one that I've heard referring to Go code a lot, which is don't make the abstraction until you have to, and don't write the efficiency until you've proven that you need it. You should probably just do the easy thing until you know that it's a bottleneck.
Yeah, I think the way I look at it in general is I'm not a fan of like a big checklist. And if I like do all these cool things and my code is good, it's just measuring what I'm working with and seeing like, well, what does it need? And like, I like to have a large menu of what I need, and pool can show up, but it's driven by the needs of what I'm doing, as opposed to, I don't know, like, I don't go through and think unrolling loops is fast. I'm going to try and unroll every loop in my code or something like that.
Gotcha.
But yeah, I agree. There are other ways to solve that problem. You don't always need to reach for a pool at the first time. I've never personally even written a pool. I just know what it is because we had a library that was vastly sped up by, I'm pretty sure it included a sync pool.
I would almost say pool is kind of the lazy way to do things if you can't like reason out how to do it in a Rust-like way. Which is to say, if you can figure out how to like more statically allocate your memory and make it more like function scoped, so that it's just, then you don't have, then that's usually better. But if you can't do that and your memory usage is a little bit more like unpredictable, then you can just reach for the pool.
Thank you. So just something to reference about that is we're covering basically 6 different overall ideas today. And the ones that really matter are mutex and weight group. And these next 4, I'm not going to cover as deeply, including pool, because it is much more rare that you'll actually need to use them. One that is, this is probably the next most useful though, is once. So the idea of once is if you want to just be able to easily define a function as only needing to run one time, you can use once. So here I have sync.once, my once variable, and I have my database initialization. And here I'm going to 10 times try to query my database. And what my query is going to do, sadly at this point, is just initialize the database. So 10 times it's going to attempt to initialize DB, and initialize DB is going to print initializing database connection. And because we have this wrapped in a once.do, instead of running 10 times, it's just going to run the one time. So an example of where this is useful, the most common one that I've seen, initializing databases or initializing configs. The idea being you don't have to initialize everything at the beginning of your program. You can offload work and just have it happen when it's needed. So the idea is you don't have to initialize all your databases at the beginning. You can just initialize them on first query, or you some way delay it. And an easy way to just track that you're only doing it the one time that you've run is to just wrap it in a once. And the handy thing about once is if instead you try to do it using, for example, a config variable initialized equals false, and then you initialize it, initialize equals true, is you could run into kind of a race where before that initialization finishes, someone else tries to initialize it, and now you have a conflict. Do I have any other, we're going to cover the other ones. Does anyone have any comments on once?
My only comment is be wary of using it to perpetuate what I think are anti-patterns, which is to honestly like package level variables. I think most of the time are anti-patterns. I don't know. I think Go perpetuated this with the standard lib too much personally for my taste, like the default Go client and HTTP and that thing is the bane of my existence. Like stop using the default client, stop using HTTP.get, like make a client for God's sakes. So I think so. Obviously the word initialize in a function, anytime I see that where it doesn't return anything, like it's almost like a code smell for me anymore. So like there are good uses for sync.once, but maybe beware of like enabling these ideas of global state or like package state, because it's usually a smell of shared state, which is almost always not what you want. I've seen it for, again, lazy initialization of things where you're like, I don't know, you may need to call this at some point. And often I see it, I don't see it with a top level function. I actually like the way you do it, which is a lot better, which is you don't expect someone to call initialize and before they call query, you just have like your thing that's going to assume it's connected every single time, tries to reinitialize. That way it kind of just lazy loads. So that's my only advice is don't overuse that to make package state, because I've been unwinding too much package state in my life to want to.
Anyone else? All right, we'll keep it rolling. So then we have once func, which has not just the obvious change, but we'll cover the obvious change first. So the obvious change is instead of instantiating a sync.once, I basically just directly instantiate the function. So sync.once func with the function built into it. And that's my initialized DB. And one of the benefits of that is if you just build it right in there, you can't accidentally call it outside of your once. And then the other benefit of it is if you have a function that panics, then when you call once func, it's going to replicate that panic every time. But if you do it with once, and I don't really know the nuances of this and would love input, it doesn't do it that way. Does anyone have anything they'd like to say about once versus once func?
Fascinating. Do you know when it was added?
No idea. Okay. Actually, that's pretty easy for me to find now that I think about it. Because I have a list of everything. So
You ever use the reify decorator in Python? Or use the reify decorator in Python?
I don't think so.
Function where like you want to get like a value and every time you want to call the function, you want to get the same value, but you don't want to actually run the function the entire time. So you wrap it in this decorator that basically calculates it once, stores it in a variable and just returns that every time. Same sort of thing.
Sounds like the same thing. Thank you. Once func was added in 1.21.
It's been around there for a little while.
And then we have two more, which is we have once value. And we have once values. So really just if you have once value, you can use it to return one variable. And if you use once values, you can use it to return two variables. That's it. And the idea is every time you call that once value, it will just return that variable. Or and if it, in case it has to be explicitly stated, the reason why, one, they don't just keep adding once value, once two values, once three values, once four values is because you can just have the first value be a struct and the second value be an error and fit whatever you want in there. And it's not too much worth covering, but the idea is just, yeah, get config as a sync once value. And then every time you want to get the config, it's just going to replicate the one time that you ran it and give it for you. Any questions? Any comments?
This one's more like that Python decorator where it can return the same value.
Yeah.
So does that just like store that return value in memory somewhere and return it every time you hit it, or?
Yeah. I mean, I say yeah pretty confidently. I think yes.
Ish.
That's how it plays when I use it. Anyone else?
Those are two functions where the implementation, if you follow it, is actually a really minimal implementation as well. Just generics with like, yeah, probably about as on par with the group.go for complexity.
Oh,
If you were to follow in and control click on once value and look at it, I'm not saying you should, but I'm saying like, my guess is you look at it, it's like a little bit of generic wrapper around a really common pattern. In lines of code. Or less.
you're right.
I love being right. Thank you.
You are. Yeah, you're dead right. It just, yeah, runs the function, marks it as valid, and if it's not valid, panics, and then returns it.
There you go.
Great. That's once. You've got two more left. This one is cond, which is condition. And we have two left. It's not going to go as long as any two that we've done before. We're going to go through these pretty fast. So how cond works is the idea of these go routines could be waiting for something to be done. And an easy way to do that would be just to basically mark a condition. And then when that condition is true, notify all the go routines that condition or that the condition is satisfied and that they can continue. And what that looks like is you create a mutex, you bind that mutex to a new condition, and then we're going to create three go functions here, go routines that are going to basically wait on the condition. So these go routines are going to reach here, they're going to walk, and then they're going to wait. And the reason you have to lock first is because wait does three things, which is, the first thing it does is releases the mutex. The second thing it does is begin waiting for the condition to be satisfied. And the third thing it does is relock the mutex. Those three things. So you have to lock the mutex. Then after the mutex is locked, you can wait on the condition. And then when you've been signaled to continue within this go routine, you can release the mutex that's been relocked by cons.wait. And down here at the bottom of this function, what we're going to do is we make those three go routines that are all going to wait. We wait for a little down here, and then we're going to mark ready as true and unlock and broadcast. And what broadcast does is it notifies every single go routine that they are ready to rock, that the condition has been met. And what this looks like is they all just proceed because broadcast hits them all at the same time. They immediately unlock the mutex because they don't really have anything they need to do with it. And then they print. Any questions on that?
You know, did they list practical examples of where this? I remember when this was added, and like it's intricate to get it right. It's the thing I remember is like the order of these is really hard to get correct. I'm just curious, like what their use case was for like we really needed this for these. You have
No idea.
okay, that's fine.
Yeah, I put it at number 5 for a good reason.
Yeah, it's fine. Yeah, it is probably the least useful broadly
Does
speaking.
it feel gross to you? Because it feels gross to me.
It feels a little bit, well, again, because it's like, they say you have to do this in this order, and that feels very
Shane-
like to like dictate the package usage.
Okay, if
You don't,
Shane's only
like,
used
very
it
minimal-
once, there's never a use case.
I mean, this is Java's for like counting semaphores. And just like you described, there's like an intricate sequence you have to follow that's hard to remember. And so I never use it, but people use it for like basically to cap something at like a count, right? Where there can, and so as opposed to there could, you know, with mutex, there can only be one, but you want, there can only be like 5. So in Go, a lot of times, because this is a little too scary, like I end up using a channel or something for that, but
I would also probably use a buffered channel for that.
Okay, yeah, because that's,
scary and weird.
it is, well, yeah, it is.
Like the better
Channels
one.
are brittle, but not this.
Not as much as
Oh,
condition
yeah, I agree.
variables. Condition variables are very classic. I don't know, CS weird stuff for me.
Yeah, I don't have any experience using these, but I've read about some highly concurrent data structures that like, you know, super crazy highly concurrent trees and stuff where you can get a lot of lock contention when something isn't ready to use it and it just needs to poll over and over again. And something like this would prevent a lot of lock starvation because you're not actually getting the locks until the condition is met. And so it's just really rare because these are like the kinds of data structures that someone writes once in a library and then just people use. There's like 4 of them.
I was gonna say, I feel like this is probably for something like deep in the standard lib, and it's really useful if you have that really specific use case. Almost nobody will, but when you do, aren't you glad it's there?
Yeah, I think that's fair.
Great. So the rule of thumb is if you're learning what this is from the presentation, don't use it yet.
That's good, that's good.
Also, I would like to comment that I appreciate that Shane, right? Shane does a lot of benchmarking. I do enjoy benchmarking the standard lib usefulness against Shane. Shane hasn't used it, don't use it.
He was the one that taught me how to even use a wait group, so.
Oh, that's awesome. Okay, well, then we will skip this next thing pretty quick, which is, so broadcast notifies everything waiting on it. Signal is just slightly different, and all it does is it notifies 1. So you can kind of start this chain reaction where when the condition is met, you signal 1 go routine, and then you can continue signaling from that point. So if you look at this change here, instead of just broadcasting and notifying every go routine that the condition's been met, we're going to notify 1. And then every go routine at the end is going to also make that signal starting the next one and letting it continue. And it's just going to look slightly different here, which is, oh, it's right at the bottom. And you can see them going sequentially. Now we're on maps. Okay, so maps is going to go really fast. And the reason why maps is going to go really fast is because they work like maps for one. And two is when I looked at the Go specification for it, at the very top, it says, do not use it. I'm not gonna get deep into it. We got a couple minutes left. It says you can use it under two circumstances, which the first one is if you are writing to keys one time. If you're just gonna write to keys but not overwrite them, then this is a nice thing to use. And the second thing it said is if your different Go routines that are accessing this map are accessing pretty discrete parts of it, where they're not overlapping the keys that they're reading or writing that often, then you can also use it. But they really just said, just take a map, take a mutex and walk away. So some of these will look, so we're just gonna breeze through it. So here's load and store. And you can just store a value with a key value pair, and then you can load based on the key and get the value and get if it exists. So key exists and missing doesn't. And here, if we store again on the same key, we overwrite the value. This is loader store. Loader store is going to, if it doesn't exist, store it and then mark false that it didn't exist before. But if it does exist, it's going to overwrite it and say true, we overwrited it. So the first time it marked false and the second time it marked true. Oh, sorry, it doesn't overwrite it. It doesn't overwrite it. It says it already exists, so we're not going to overwrite it, and I'm going to return what the value was. That's what that does. Delete is the ability to delete a key. Load and delete will return the value and then delete the key value pair. Range is the ability to just iterate using a function that takes key values and returns a bool and allow you to iterate over your map. And if you ever return false, it'll quit the map and return the map. It's the range itself can return false. Sorry, not quit the map, quit the range. We've got swap. And what swap does is it allows you to grab a value and then replace it with a different value. And then we have this little nifty difference, which is you can see here, it grabbed the value, it returned true that it existed, and then switched it with new. And over here, because I deleted the store, it said it doesn't exist, but then stored it, created a key value pair. And if this is too fast, that's probably good news for you because you don't want to use it. And then we have compare and swap. And what compare and swap does says you give a key, you give a value, and if that key value pair matches, replace the value, right? So we have key and old, and because we have key and old, we can replace old with new, but when we try key and old again, that doesn't exist, so it doesn't replace it with newer. You can see true for the swap, false for that swap not working, and new is the new value of that key. Compare and delete is pretty similar, so if the key value pair matches, it deletes it. And then we have clear, and clear just empties the map. And that is the entirety of the sync package with the absence of the atomic package.